Okay, we'll move on to Chapter 3, the classification of matter. Now, matter, something we talked about in a prior chapter, is material that makes up all things. If something takes up space and has mass, it's made up of matter. So anything that takes up space and has any kind of mass is considered to be matter. Now, matter can be classified according to its composition. A pure substance is something that has a very definite composition or a fixed composition. There's also a mixture, where you have two or more different substances that are physically mixed but are not chemically combined. And we'll talk more about that in a second. Okay, we'll talk about a pure substance first. It's classified as a type of matter that has a very definite or a fixed composition. An element is a very good example of that. Any element, say on the periodic table of elements, all that is found in that element are those particular atoms. So you only have one atom, say in a mass of aluminum or a mass of carbon or so on. There's nothing else found in that sample. When you have two or more elements combining, that's when you form a compound. So a compound is two or more elements that are always found in the same proportion. Like we just mentioned, elements are a pure substance that contain only one type of material. Copper, lead, aluminum. If you have, say, in this example, a copper penny, there's no other element, no other material found in that penny other than copper. You won't find calcium, you won't find potassium, you won't find helium. All you'll find there is copper. It is a pure substance. And again, in compounds, two or more, it has to be at least two elements, and there's no limit on how many there can be, but there has to be at least two elements that combine. And they combine in a very fixed ratio. And here's some common examples. Hydrogen peroxide, H2O2, table salt, sodium chloride, sugar, C12H22O11, and then water, H2O. And here's what I mean by a fixed, definite ratio. Let's compare hydrogen peroxide and water. Very, very different substances. Water, obviously very safe to drink, H2O. Hydrogen peroxide is very dangerous, very toxic, so it's something that you would not want to drink. So the formula for hydrogen peroxide, H2O2. For water, H2O. The only difference chemically in these two compounds is there's one more oxygen here in hydrogen peroxide. So if you start with this and take away one of these oxygens, you get H2O, water. So just by removing one element will mess up that ratio and will give you a resulting totally new compound. So same thing with water. If you take away, say, a hydrogen from water, you end up with hydroxide, which is completely different than water. So compounds are in a very definite, very fixed ratio. So anytime you have H2O in a compound, this will always give you water. This will always give you hydrogen peroxide. This will always give you table salt or sodium chloride. This combination will always give you sugar. It can't be anything other than those. Alright, we just talked about table salt. Table salt is a compound that combines the elements of sodium and chlorine. When they form together, sodium chloride, that forms table salt. That's a very good example of a compound. So sodium and chlorine will form the common table salt. Alright, next move on to mixtures. A mixture is a type of matter that will consist of two or more substances that are combined physically but not chemically. And these are two or more substances in different proportions also. And key thing here is that they are physically mixed and can be physically separated, but they're not chemically joined. Think of this as a big bowl of M&Ms, where you have some red, some green, some brown, some yellow. They're all in the same space. They are physically connected, but they're not chemically bonded to each other. You can separate the reds from the greens, from the yellows, and so on. Right, there are different types of mixtures. Homogeneous mixtures. Prefix homo means the same. So for this type of mixture, the composition is uniform throughout the entire mixture, and the different parts that make up this mixture are not visible. And the example that's given here is brass. Brass is a combination of copper and zinc. So when you see this picture of a brass vase, all you see is brass. You don't see the zinc. You don't see the copper. You see what results in their combination together, which is brass. All right, another type of mixture is called heterogeneous mixture. Prefix hetero means different. So in this type of mixture, the composition will vary from one part of the mixture compared to the other, and the different parts of these mixtures are visible. The example that's given here a glass of water and copper. You can see the water, you can see the copper. They are still mixed together, but you see the individual components that make up that combination. All right, next we'll move on to the states of properties of matter. And the first one we'll talk about are the solids. Now, solids have a very definite shape and a very definite volume. The particles that make up solids have a very fixed arrangement, and they're very, very close to each other. Anything that is solid has a definite shape. It doesn't change the shape varying on its container or where you put it. A textbook doesn't change shape because you put it in, say, a shoebox or a backpack or a suitcase. It stays the same definite shape. Volume doesn't change, the shape doesn't change because the particles are so compacted together inside it. So this block of amethyst here won't change its shape no matter where you put it. All right, next move on to liquids. Liquids have an indefinite shape but a definite volume. A liquid will take the shape of its container that it's placed in. So for this example, you have 3 glasses of water. The glasses are different shapes, so it will take the shape of the container that it is placed in. The particles are close to each other, but they're able to move by one another, and these particles tend to move slowly. Let's say if you were to take a liter of water and pour that water into a 2-liter plastic bottle and pour that volume of water into a bathtub. The volume is still the same, but the shape will be very, very different. So again, it is the container that the liquid is in that will determine its shape. All right, gases, these have an indefinite shape and also an indefinite volume. They take the same shape as their container that they're in, just like a liquid would. These are considered fluids. So a gas and a balloon take the shape of that balloon. The particles in gases are very, very far apart, and they move very, very fast from one another. All right, next we'll talk about physical changes. A physical change in a substance is where there is a change in shape or a change in the state. We'll talk about what those are here in a second. But there's no change in the chemical makeup of that substance. Chemically, it's still the same, it just looks a little bit different. All right, some common examples of physical changes. Water boiling to form water vapor. All forms of water, whether it be liquid or solid or gas, think of a glass of water or an ice cube or water vapor. Those are in 3 different states, but it's still water chemically. So it may look different, but it is still a form of water. Those are physical changes. Some other examples of physical changes: paper is cut into tiny pieces to make confetti. It is still paper. It may be really, really small pieces, but it is still chemically a piece of paper. Copper being drawn into thin wires. It may be thinner and longer, but it is still copper. Chemically the same, but physically it looks different. Next, move on to chemical changes. When a chemical change happens, you are forming a new substance with new chemical properties and new physical properties. A good way to think about these are things that cannot be undone. Or you have physical changes, some of them can be undone. You can freeze water, or you can evaporate water, or melt ice. You can change the physical state of water, even though chemically it's still the same. You can change physical changes, but chemical changes can't be undone. As an example here, mounds of sugar being caramelized. You can't unburn something. By caramelizing the sugar, you are giving it new chemical properties. You're giving it new physical properties. You are making something different and new. Some other common examples for chemical changes. A silver metal is shiny. Once it's exposed to air, will eventually give you a black grainy coating as silver starts to tarnish. And is chemically something different. And you can't undo that. Burning a piece of wood or burning anything makes a new compound, makes new material. So that is a chemical change. You can't unburn something. Same thing with this last example here. Iron mixing with oxygen to form rust, especially over time. You can't undo that. That is a chemical change. It may look different physically also, but chemically it is something different. It has new properties and it is a new compound. Now we'll move on to temperature. Temperature is a measure of how hot or how cold an object is compared to another object. And this will indicate the heat flow from an object from a higher temperature to an object that has a lower temperature. And of course, a thermometer will be used to measure temperature. We've already mentioned briefly the 3 types of scales used to indicate temperature. One we'll talk about now is the Kelvin scale. The coldest possible temperature that is known is negative 273 degrees Celsius. That's known as absolute zero. At that point, the particles in that material stop moving and cannot generate heat, so there is no temperature beyond that point. This is also represented by 0 Kelvin. Not 0 degrees Kelvin, but just 0 Kelvin. One thing that's a little bit different from Kelvin compared to the Celsius or Fahrenheit, there's no negative temperature reading for the Kelvin scale. The lowest you can get is 0 Kelvin. And also has the same size units as the Celsius scale. So 1 Kelvin would equal 1 degree Celsius. And this formula here is a way to calculate a given temperature in Fahrenheit, how to convert that to a Celsius scale. What you do is you take that temperature as given, let's say it's 113, you subtract 32 from that Fahrenheit temperature and divide that total by 1.8. So 113 degrees Fahrenheit would give you 45 degrees Celsius. Alright, on this image we have the comparison of the three major scales for temperature and what goes on at key points for each. I will start here on the Fahrenheit scale. The freezing point where water freezes, 32 degrees Fahrenheit. Also the same thing as 0 degrees Celsius, which is also the same thing as 273 Kelvin. Normal body temperature in the Fahrenheit scale, 98.6. In Celsius, 37 degrees Celsius. And for Kelvin, 310. The boiling point of water in Fahrenheit, 212 degrees. For Celsius, 100. And Kelvin, 373. Now it's important to remember that even though there are three different scales used, the temperature being measured is exactly the same. So the amount of heat generated, say, by 98.6 degrees Fahrenheit is equivalent to 37 degrees Celsius, which is also equivalent to 310 Kelvin. So it's exactly the same quantity being measured, but using three separate scales. Alright, next move on to energy. Now, energy is what helps make objects move, makes things stop, and has a formal definition of the ability to do work. And there are different types of energy. One is kinetic and one is potential. Kinetic energy is the energy of motion. Kinetics is always a reference to things moving. Water moving or a car moving. Anything that has any kind of motion has kinetic energy. The opposite of that would be potential energy. This is where you have energy stored to be used later. Water being blocked by a dam. A spring being compressed, pulling back on, say, a rubber band. Your storing energy is not being used for movement yet, but it's being stored for use later. It has the potential to make kinetic energy. Moving on to heat and energy. Heat is the energy that's associated with the movement of particles in a substance. The faster the particles move, the more heat that gets generated, or the more thermal energy is generated. Alright, let's say you're given an ice cube, and because it's a solid, the particles tend to move incredibly slow. If you were to add heat to that ice cube, that will cause the particles to move much faster. And as those particles move faster, they generate more heat that will change their state from a solid into a liquid. That's how you get from a block of ice into liquid water. The particles inside that ice cube are being moved so fast that they actually break the bonds that hold them together and turn it into a liquid. Energy is measured in the International Systems Unit by the unit called joule, abbreviated by the capital J, or can also be used in what's called kilojoules, lowercase k, capital J. Remember, kilo always means 1,000, so a kilojoule is 1,000 joules. You can also use the term calorie or kilocalorie. Those are also units of measurements for heat. Now, the actual definition of calorie in the formal sense, in the technical sense, is the amount of energy that's needed to raise the temperature of 1 gram of water by 1 degree Celsius. To compare a calorie to a joule, 1 calorie equals 4.184 joules exactly. And here's a comparison. If you're given one, it can convert to the other. But notice that the C in calorie is lowercase, and that's important. It's something we'll talk about next. Now, when I say calorie, most people think of the calories in the food that they eat. And this is a term that gets misused all the time. In science, the calorie is what we just talked about, what it takes to raise 1 gram of water 1 degree Celsius. That's used in physics, in chemistry, and biology, that is a real scientific term, calorie, lowercase c, CAL. But when you talk about calories in food, what you're really talking about are food calories. And that's written by, or indicated by, a capital C. And what this really represents is 1,000 calories, or a kilocalorie. So when you read, say, food labels like this at a grocery store or in your kitchen, what you're really reading is kilocalories, or 1,000 calories. So kcals. So when you talk about calories from food, you should indicate that it is a food calorie, or use a capital C to indicate that it is a kilocalorie, not a regular calorie unit in science. Right, next, move on to what's called specific heat. A substance such as water has a very high specific heat, which helps keep temperatures more moderate in the summer and the winter. And this can vary greatly, specific heat by substance. And the definition of this is the amount of heat that is needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. And it can vary greatly depending on the type of substance that we're referencing. And this goes into how well an object can be heated, how much it can be cooled, how much heat can be transferred from one material to the next. Here are some examples of some common elements and common compounds and their specific heat. Say aluminum, a solid piece of aluminum, 0.214 calories per gram, degrees Celsius. Copper, much lower, 0.0920. Gold, 0.0308, and so on. Of course, water is 1. When it's a liquid, and when it's a solid, like an ice, it's going to be half that amount. Alright, now we'll talk a little bit more about a changing of state. This is when a material gets converted from one state to another, from a solid to a liquid or to a gas, whenever you are changing a physical shape or a physical state. There was something being melted, something being vaporized, something being frozen, and so on. Alright, a substance is considered to be melting when it reaches its melting point, or MP. This is the temperature at which it will turn from a solid into a liquid. So when that block of ice starts to become liquid, that is its melting point. And of course, the opposite of that, the freezing point, or FP, is where a liquid turns into a solid. When that glass of water turns into a ice cube, it's become moving from one state to the next, from liquid to solid. All right, move on to the heat of fusion. This is the amount of heat that it gets released when a gram of liquid freezes. So that's freezing point. You'll have a release of heat, a release of energy. Also, the amount of heat needed to melt 1 gram of a solid at its melting point. So for example, water, the heat of fusion is 80 calories per gram of water. Alright, next we'll compare evaporation, boiling, and condensation. Of course, we'll talk about water. Water will evaporate when the molecules on the surface gain enough energy where they are converted into a gas. Remember, the particles of liquid move kind of slow. So as the particles of water are heated enough, particles will move around so fast they will actually convert and change state into a gas. Now, when the opposite of that happens, when that gas will start to lose energy, those particles will start to slow down, and they will collapse together and form a liquid, what's called condensation. Right, when water is boiling, all of the water molecules acquire enough energy to form a gas, what's called to become vaporized. Of course, during boiling, the molecules of the liquid are converted to gas throughout the liquid, as well as on the surface. So not just the bubbles you see on the surface bubbling, all the particles inside that substance or water are boiling also. Right. Heat of vaporization. This is the amount of heat that's absorbed to change 1 gram of liquid to gas at the boiling point, and also the amount of heat that is released when 1 gram of gas changes to liquid at the boiling point. So for water, 540 calories per gram. So say you're starting with the liquid water here. When you add heat to that, the particles will start to move faster and faster to the point where they are very, very far apart and they become a gas, where they are vaporized. All because you're adding heat, making the particles move faster. When these particles start to lose energy, when heat is taken away, they will condense to form liquid. So going from a gas, water vapor, to liquid water, condensation. So it all depends on how much heat is either introduced or taken away. All right, next we'll talk about heating and cooling curves. Here's a common example of a heating and cooling curve here. You're given information on when a substance turns from solid to liquid and from liquid to gas, and when they're basically changing states and at what temperature, and how much heat is absorbed. These diagonal lines here indicate a change in temperature for a physical state, and these plateaus here and here indicate the actual change of state. Let's say you have solid water here, a block of ice. As it starts to melt, it goes here. Then you start to introduce more temperature, more heat. So you see the temperature increase over time, and the more heat gets absorbed. At this point, it will start to boil. As more heat gets introduced, more energy to the particles, so they move faster, and it becomes a gas. So, of course, the opposite of that would be the cooling curve. It shows you where the physical states change from gas to liquid and from liquid back down to solid. So for the chart on the previous slide, that shows you how heat was added over time. And for here, it's the exact opposite. How heat gets removed, which will remove energy from particles, which will make it slow down, which will make a gas turn into a liquid as it condenses here to a liquid. And from here, getting even more and more slow with the particles, it becomes a solid or ice. Thank you for watching our newest video on our crash course in chemistry. We'll have new videos in this lecture series every Monday and every Friday of each week. So stay tuned for our next video in a few days. And don't forget to subscribe to this channel so you can be notified of when our new videos are posted each week.